All right, welcome. How's everybody? Good. Okay, so my goal for today, finish up chapter 3 and start chapter 4. So I hope you're going over the chapter 3 stuff. This handout from last time, so that should give you a pretty good handle on what to focus on with the chapter. The page numbers from the textbook are noted in parentheses here, so we worked our way through almost everything, coming up on the last part here, so 76 through 78 right here. So do you have any questions on that? This is not something I'm having you turn in. I just want you to begin studying now for the next exam and just know what should be emphasized with your study. So, okay. Okay, so with that, we've been talking about lactic acid and myths and misconceptions that continue to be spread throughout the training community. So this is a short assignment that you'll do over the weekend and will be due on Tuesday. So you can find this assignment. So going to the course homepage. You can find this under the assignments folder. So you scroll all the way down, and then Thurs Oct over 6 lactic acid web reads, and then you can open it and then click on the link. And hopefully it works. It does. So lots of good information on what the role of lactic acid or lactate is in exercise and training. Another good link right here. Debunking myths about lactic acid fatigue and recovery. So both awesome articles. You'll just read and then just have brief responses to those questions there. So that'll be due on Tuesday. But for now, we've got chapter 3 to finish up with. Do you have any questions? Okay, so anaerobic performance, peak power, mean power, fatigue index, all of these things that we look at. So those of you in Tuesday lab did the step test. Depending on the stairwell you choose, that will affect the vertical displacement, right? And then divided by the time, and then multiplying the vertical displacement by your body weight. So what that says is that mathematically with power, if power is force times displacement divided by time, but you can't do anything about the displacement unless you choose a different stairwell. If the displacement's always going to be constant, then a larger individual or being able to climb those 6 stairs in less time is what's going to maximize your power output. So just doing some quick calculations, you remember the number we multiplied by body mass to get our weight in newtons? Yeah, 9.81. If you want just a quick way to convert that, you can just use 10 in this case. So if you're a person that has a body mass of say 95 kilograms, and rather than 9.81, you can just substitute 10 to make it easier. So 95 times 10 is 950, so that's 950 newtons. So 950 newtons divided by, let's say, going from step 3 to step 9, you did that in 0.6. Okay, so that's going to give you a power output of 1,583 watts. So the weight that you have and the displacement divided by the time is crucial. So getting up those stairs really fast is the key. So let's say you have a mass of, say, 55 kilograms. We'll multiply that by 10 to get 550 newtons. Multiply that by, let's say, you have a vertical displacement of 1 meter, so it's really not going to change, right? So that's 550 newtons divided by, let's say, 0.5. If you're really quick, that's going to give you a power output of 1,100 watts. So quick, easy assessment for power output, very practical. You can use it on large numbers of people. Wind gate test gets a little more complicated because you're talking about, hey Michael, you're talking about a bicycle and the number of revolutions. And so for distance, in the case of the wind gate bike, it's 6 meters every time the pedals go all the way around, 360 degrees. So 1 revolution is equal to 6 meters. So if we go back and take a look at the wind gate test, so this is just an example wind gate test. And so you can see all of the preliminary information that we want to know right at the top. So we're talking about an individual that has a body mass of 58.5 kilograms. So that would correlate to a certain degree to the amount of muscle mass that you're using to pedal the bike. And the resistance for the legs, okay, so it's 7.5% of your body mass. So you'll all have the opportunity to do this. So take your body mass times 0.075 and the amount of resistance in the basket. Do you remember the basket from the bike in the lab? So in this case, for this person, it's going to be 4.4 kilograms. So you'd have 4 of those thick 1 kilopond, which is the same as a kilogram. You'd have 4 of those, and then you'd have 4 of the fractional plates that each have a weight of 1/10 of a kilogram. So that's what this person, at least, was pedaling against for 30 seconds. So to review, at what point does peak power take place during a wind gate test? So you have to get, the rules for the wind gate test, you have to get the pedal revolutions up to at least 90. So why is that important? Rather than just starting from a static start. And it's a good thing, because that's a lot of mass to pedal against, right? So if you're just starting from a static start, that's overcoming a lot of inertia to get those pedals moving. So without any resistance, with the basket up, you get those RPMs going to a minimum of 90. You can go faster if you want to, and then on your, it's up to you, and you drop the basket, and then you're engaged for that 30-second test. Hard as you can go. So right out of the gate, we're looking at peak power happening somewhere within about the first 5 seconds. So in this case, we can see peak power happened between seconds 2 to 6 was when it happened, and we can tell. How can we tell? That's where the peak power was at. Because that's where the revolutions were the highest, right? So you could assume that that's where the peak power happens. So for peak power in a wind gate test, go ahead and take out a sheet of paper for this part. So we can get our engagement going for today. So for peak power for the wind gate test, you'll want to know how much resistance. So capital PP, that's peak power, is equal to 4.4 kilograms, because that's how much resistance was in the basket, okay? So 4.4 kilograms multiplied by, what's our distance per revolution of the pedals? Yeah, 6 meters per revolution. Okay, so 4.4 kilograms times 6 meters per revolution. And then what was the peak revolutions? It was 10.25. So if you look all throughout the test, that's where they had the most revolutions in any given 5-second interval. So peak power, how much resistance, the amount of distance covered per revolution of the pedal. So all the way around, that's 6 meters. So 6 meters per revolution, and then multiplied by 10.25 total revolutions. And that's going to give you the peak power. So what cancels is the revolutions, and you're left with, what are we left with? Kilogram meters. Kilogram meters is what we're left with. So why don't you multiply that out and see what you get. So this is over a period of 5 seconds. So what did you come up with?
270.6?
Yes, 270.6 kilogram meters in 5 seconds. Okay, so now follow me along here, because a lot of times in exercise physiology, we like to look at things not in terms of 5 seconds, but over the course of a minute. So do you notice how we have lots of things in exercise physiology that are measured per minute? Like we have VO2 that's milliliters of oxygen per kilogram of body mass per minute, right? Okay, cardiac output, liters per minute, and so on. So oftentimes we like to prorate things up to the full minute. Okay, so you have 270 kilogram meters per 5 seconds. So to prorate that to a whole minute, we have to think, okay, so how many 5-second intervals do we have in an entire minute? So how many 5-second intervals do we have in one entire minute? 12. Okay, so we can prorate 270 kilogram meters to an entire minute simply by multiplying 270 by 12. So all we're doing is prorating a 5-second value up to 1 minute, because that makes things easier to work with eventually. So why don't you go ahead and do that? 270 kilogram meters multiplied by 12, and you're going to get a big number. You're going to get a big number, but that's okay, because we want to prorate it to a minute. So go ahead and work that out. So 270 kilogram meters in 5 seconds, so you multiply by 12, and you get a certain value of kilogram meters per minute. Kilogram meters per minute. So what'd you get?
3,247.2.
Good. 3,247.2 kilogram meters per minute. Okay, so that's a lot easier to work with. So that's an absolute value. So what if you have two individuals and they both had that same value on their test? So 3,247.2 kilogram meters per minute. How would you know which one is actually better? What would you have to take into account that we haven't taken into account yet? Yes! Very good. Sharp. Okay, so what's their body mass then? Yeah, 58.5. So Now all we do is divide that 3,247.2 divided by body mass of 58.5, and now we have a relative value. Now we have a relative value. So you can compare two individuals with the same score. We can compare relative to their body mass to kind of learn more about their fitness level. So we do this all the time. So how many of you have ever maybe thought about, okay, so you have the same body weight as another athlete, so you compare strength relative to body weight, so pound for pound strength. Yeah, so we do that all the time. It's the same idea here, only this is more of a power test. So peak power output relative to body mass. So what'd you come up with? Dividing 3,247.2 by 58.5, and now what are we at? Yeah, 55 kilogram meters per minute per kilogram of body mass. 55.5 kilogram meters per minute per kilogram of body mass. So we're starting to get into a lot of units, aren't we? So what is our unit for power? What do we ultimately want as our unit for power? So the Margarita-Kellerman test, you ultimately came up with a value that you looked at in the normative table, and what was the unit for the value in the table? Watts. So how do we get there? Okay, so here's how you get there. So for a cycle test, there are 6.12 watts per kilogram meter per minute. 6.12 watts per kilogram meter per minute. So if we divide that value, you said 55.2? 55.5. If we divide 55.5 kilogram meters per minute per kilogram, it's a lot of units here. If we divide that by 6.12 kilogram meters per minute per watt, we'll come out with watts per kilogram is the value. So divide 55.5 by 6.12 and you come out with watts per kilogram. Watts per kilogram. So it should be, well, 6 times 9 is 50. It should be 9 something. What'd you get? Yeah, 9.07 watts per kilogram. Per kilogram is what we're left with. So do you see how everything cancels except the watts per kilogram is the idea? So what I just took you through there is the complete process. So if we know this information, how do we get peak power? So the highest of the high. So mean power then, what's mean power versus peak power? So the peak power considers the highest 5 seconds. What about mean power? Considers all of it. So mean power implies that at some points power output was higher, at some points power output was lower, but for the 30 seconds as a whole, on average, this was what power output was. So rather than taking 10.25, we have to take the total number of revolutions. So a week ago, remember when I asked you to painstakingly count all those revolutions? Do you happen to remember what value you came up with? No, I'll just tell you. You all came up with 45.25. So in 30 seconds, this person spun those pedals 45.25 times. So to follow that same process, we can just say, okay, so how many kilograms So mean power now is 4.4 kilograms, because remember that's how much they're pedaling against. Okay, and then how many meters per revolution? 6. Okay, so same process, 4.4 kilograms times 6 meters per revolution times 45.25 total revolutions, and that gives you your mean power. At least it gives you us a start, because we have those other steps that we have to go through. So it's going to give you a great big value. So 4.4 times 4.4 times 6 meters per revolution times 45.25. What'd you come up with? 1,194. Good. Okay. So what's the next step? What do we need to do now? So we need to prorate it to a minute, right? So let's just, same process. So before I asked you how many 5-second segments are in a minute. So now, how many 30-second segments are in a minute? 2. So then you take that value, just like we did before, only now it's mean power. So you take that value that you got, 1,000, multiply it by 2 to get kilogram meters per minute. Kilogram meters per minute. So then we have to take that number, so that number relative to body mass. So then we're dividing by 58.5 again. So it's the same process, only you're going to get a lower number. So what was it? 2,000, remind me, 2,000? 389.2 kilogram meters per minute divided by 58.5 kilograms. So you come with kilogram meters per minute per kilogram. What did you come up with? 40.8 kilogram meters per minute per kilogram. So how do we get rid of all those units? Because there are 6.12 kilogram meters per minute per watt. And you divide the 40 point whatever it was by 6.12 to get watts per kilogram. So that's your final value. So isn't it nice that we have software in the lab that just does all this for you? So this is the only, I asked you to do this once because I want you to understand how it works. But after that, we just use the software. So what'd you come up with? So we had, how many? 9.07 watts per kilogram was our peak power. What was our mean power? 6.7 watts per kilogram. So can you see how the mean power ends up being lower than the peak power? Which makes sense. Okay, so let's figure out fatigue index then. So fatigue index, the formula is, okay, so it's going to be 1 minus, so write that down first, 1 minus, it's going to be the parentheses, so 1 minus, open your parentheses, lowest power output in 5 seconds, divided by the highest power output in 5 seconds, close your parentheses, multiply by 100. So let me say that again. So 1 minus, and then open parentheses. You're going to take your lowest power output in 5 seconds, divided by your highest power output in 5 seconds, close your parentheses, and then multiply by 100. So we already have the highest power output in 5 seconds. So that was the 270 way back, very first calculation we did, 270 kilogram meters in 5 seconds. That was our high. So what we have to do now is calculate what the low was. So tell me, how do I do that? How would I determine out of that entire 30 seconds what the lowest power output would be? Where would I look for that? Yeah, so you can just say, okay, pedal revolutions, 5 seconds, so 10.25, and then we are running out of gas. You all experience this where you're trying your very best to hang on, but it's dropping. Muscles are fatiguing. So way down here, the very last 5 seconds, turning the pedals 5.5 times. So the lowest power output in any given 5 seconds, we can use this 5.5 value. So 5.5 revolutions times 4.4 kilograms times how many meters per revolution? 6. So 5.5 times 4.4 times 6. Is everybody okay at this point? What values and why? So then you multiply those together and you get the lowest kilogram meters for any 5-second interval. What did you come up with? 145.2 kilogram meters in 5 seconds was the lowest value. So now we can go ahead and do the math. We have 1 minus, and we want to do the stuff in parentheses first, right? So 1 minus whatever value you get in parentheses. So it's going to be 145.2 divided by 270.2, correct? 270.6. So 1 minus whatever value you get in parentheses, multiplied by 100, and you should come up with a value that reflects the percentage drop in power between the first of the test and the last of the test. The percentage value, the percentage drop in power, which is a good index of fatigue, right? What percentage are your muscles dropping in their power output between the first and the last of the test? So what'd you come up with? Yes, very good, 46%. So the power output from the first of the test is dropping about 50%, almost 50% by the end of the test, which actually isn't bad. That's really pretty good. So you get some athletes that are very anaerobic, very fast twitch oriented, that have this massive value of, huge value right out of the gate, where they're going and pedaling, 13 revolutions right out of the gate, and then they're just sinking like a rock at the end of the test. And so they're ending up with a drop of about 65% by the end of the test, which reflects what their muscles are. They're very explosive and fast twitch type muscle. And then you have more endurance athletes that are down in the high 30s, so they're not dropping very much at all between the first and last of the test. So do you have any questions?
I'd be curious to see what it would be for the fastest sprinters in the
Yeah,
world.
probably, I would expect. We've had some very good, not elite, but some athletes that have really killed it the first 5 seconds, and then it's just really tanked the last little bit. So we'll see. Okay, so that leads us to this part right here. So anaerobic threshold as defined by Wasserman. So again, noting the page number, page 74. So if you were to look there at page 74, so if you do have your book, you're welcome, electronic or hard copy, to follow along. So it's right at the top of page 74, first column. So anaerobic threshold is defined as the exercise intensity, usually described as a percentage of VO2 max or absolute workload above which blood lactate levels rise, and minute ventilation increases disproportionately in relation to oxygen consumption. So let's go over that to start with. Okay, so why would blood lactate levels begin to rise at a certain intensity? What do we know? What's going on? So we're going from oxidative dominant, exercise intensity keeps rising. Eventually, we can't supply enough energy aerobically, so what do we have to do? Where do we get the extra ATP? You gotta go with the anaerobic. So the anaerobic is a supplement to the aerobic in this case. So intensity rises enough, we cross the threshold where we start to break into glycolytic. So the end product of the glycolytic pathway, we go through those 10 steps to pyruvate. Oh, pyruvate's not able to get into the mitochondria because mitochondria are maxed out, but we've still got to have that ATP, so we want to keep breaking down glucose to make quick ATP. What happens to pyruvate? Becomes lactate. Okay, so as you'll find out with your assignment this weekend, and as we've reinforced in this class, is lactate really the problem? No, whether you go with a classical view or the new view, what is the problem? Hydrogen ions. That's what produces an acidic state. So release of excess hydrogen ions at a rate faster than we can do what? Pick them up, neutralize, buffer. Okay, so you have an upset stomach. So what do you take for an upset stomach because of excess stomach acid? What do you take? A Tums. So are things in our muscles that serve as a Tums for our muscles? Yeah, our body has natural buffers. So what is meant by that term antacid? An antacid is anti-acid. So our body makes natural buffers, and there's ergogenic aids, supplements and so on that have been shown to influence our body's ability to buffer a little bit. So one of them is this substance right here, sodium bicarbonate, baking soda. Okay, so you have baking soda in your cupboard at home. Most of you, right? You can do all kinds of things with it, brush your teeth with it, buffer your muscles with it, whatever. So, but your body makes bicarbonate. Okay, but there's also studies that have had people take sodium bicarbonate, baking soda, with the intent of improving their buffering ability. So it's all about neutralizing these hydrogen ions that make things acidic. So here's the basic reaction. So it's, like I said, right here in your textbook, page 74. You're getting a full explanation there to supplement what we do here in lecture. So here it is. So you have the lactic acid here, and the sodium bicarbonate combines together. So we're neutralizing the hydrogen ions to make sodium lactate and carbonic acid. Carbonic acid is a much weaker acid. Okay, at this point, carbonic acid dissociates to water and carbon dioxide. So this is one avenue that we have to get rid of those excess hydrogen ions, simply through respiration. So when you're doing very hard, high-intensity exercise above anaerobic threshold, what's your respiration like? In other words, from this quote, he says, blood lactate levels rise. Okay, so we talked about that part, and minute ventilation rises. Minute ventilation, so the volume of air breathed per minute. So there's another value. We measure the amount of air you breathe in a minute. So again, what's your breathing like? Is it nice and slow and steady? No, it's almost like you're hyperventilating at some points if you're working really hard. So the rate and depth of breathing goes into that minute ventilation. So you're breathing more frequently, you're breathing deeper. The purpose of that serves a buffering mechanism. You are blowing off all of this CO2. So this is non-metabolic production of CO2. That's important, non-metabolic production of CO2. That means we're not producing this CO2 in the process of ATP formation. So do you remember with the Krebs cycle and with prior to that, conversion of pyruvate to acetyl-CoA, and then we go through the Krebs cycle with acetyl-CoA. We are producing CO2, aren't we? As part of that, that's metabolic production of CO2. So this would be non-metabolic production. This would be for the purpose of buffering these hydrogen ions, is the reason. Any questions on that part? Okay, so this buildup of carbon dioxide is the strongest stimulator of ventilation. That's going to really get your breathing rate up. It's when you're producing, when you're above the anaerobic threshold, glycolytic pathway, hydrogen ions that are converted eventually to CO2 that stimulates this breathing response. Okay, so the ventilatory threshold, speaking of ventilation, so is it any wonder that what's happening in the blood is tied to how we breathe? That's an important connection. So one of the ways that we can tell where the anaerobic threshold is where we have this ventilatory break point. So during the course of an exercise test, okay, so you'll all experience this when we get to VO2, your ventilation is assessed in liters per minute. So that's the volume of air going in and out of your lungs per minute. So it's kind of comparable to cardiac output. Do you remember cardiac output from maybe a previous class? That's the volume of blood that the heart pumps per minute. So you notice everything goes back to that minute value. So we like the minute value to compare things. So ventilation in liters per minute, the amount of air you breathe per minute. This is the oxygen consumption in, again, liters per minute. This is lactic acid production. So again, regardless of what theory you take, even if it's the classical theory, what happens to this lactic acid? What does it do? At physiological pH near 7, as soon as it's produced, it splits into what? Okay, so maybe we need to go back. So as soon as it's produced, let's go back to the old view, new view. Okay, so classical view, at physiological pH near 7, lactic acid does what? Dissociates to lactate and a hydrogen ion. Lactate is not this evil force inside your muscles that's causing all kinds of trauma and damage. It's simply a temporary energy substrate. Because we have tissues like the liver and the heart, and we have what's the cycle for lactate? Think of Corey back there on the back row. Corey's cycle, okay? For lactate, where the muscles take lactate, put it into the blood. What's the lactate transporter? MCT, what's that stand for? Okay, so monocarboxylate transporters, we put it out into the blood where it can go to the heart or to the liver. The liver is incredible because it takes almost anything and converts it to what? Glucose. And then what do we do with the glucose? We transport it back to the muscles. So it's that cycle. Okay, so hydrogen ions that create the problem. Okay, new view. Okay, lactate production is good. It delays muscle fatigue because it recycles NAD. Okay, so NAD is pretty much useless unless it can do what? It has to get rid of those hydrogen ions. So what does it do? According to the new view, it gives those hydrogens to pyruvate, which is then converted to lactate. So that's the new view. But regardless, old view, new view, it really just comes down to hydrogen ions. That's the problem. Okay, so getting back. So we have this rise in lactic acid. You can think about it, lactic acid, lactate interchangeably because we know that eventually it becomes lactate anyway. So this is your anaerobic threshold right here. So eventually exercise intensity is rising, and we can tell it's rising because oxygen uptake is rising. So more intensity means more oxygen, right? So eventually the intensity rises to a point where we cross this threshold, where it's not just oxidative predominant. We have to have the extra assistance in ATP production from the glycolytic system and the phosphagen system. So at this point, what happens, we cross that anaerobic threshold, what happens to our CO2 production? Non-metabolic production of CO2, we've crossed the anaerobic threshold, we're producing lactic acid. What's our CO2 production going to be like from the last slide? It's going to go up. As soon as we cross that threshold, things begin to get more acidic because of hydrogen ions, and so we're producing more CO2.
So that is, so this, is what happens at the threshold.
Yep. So the buildup of carbon dioxide is the strongest stimulus for ventilation. So if you cross that threshold, you're producing a lot more carbon dioxide. That's the strongest stimulus for ventilation. And so at this point, we have this break point. Why do we call it a break point? Because you have a disproportionate increase in ventilation relative to oxygen consumption. So can you see how at this point right here, all of a sudden ventilation starts to accelerate? So look at the definition. Refers to the point during exercise at which ventilation starts to increase at a faster rate versus VO2 or oxygen consumption. Ventilation starts to increase at a faster rate than oxygen consumption. So that suggests we are in the glycolytic pathway. That suggests we are making lactate, which means protons, which means more CO2, which means ventilation's going up disproportionately to oxygen consumption. So during an exercise test, we have that software where we can actually see that point. And so during an exercise test, Dr. Schaefer and I, we can pretty much see where you have maybe 2 minutes to go. We don't tell you that, but once you reach that point, how long can you stay in that anaerobic zone before exhaustion? A couple minutes is all. So we know once we see that ventilation start to spike like that, we know that you've entered the anaerobic zone, and it's going to be a couple minutes before that's the end of the test. So there's these indicators that we see that can tell us non-invasively, just based on your breathing, what your metabolism is doing. Okay, so does that make sense? You see the connections? Okay. All right, so why does metabolic acidosis create fatigue? So let's talk about what hydrogen ions do. So pages 76 to 77. So it's great. I would really dive into your textbook and incorporate this knowledge. So first problem, PFK, what does that stand for? Yeah, phosphofructokinase. What's significant about PFK that we learned before? That's the bottleneck. So if you take that out, what's your breakdown of glucose going to be like? If it's slowing down even more, not good. That's fatigue because you don't have ATP, because you need this to get the ATP. And if this is being inhibited even more than it already is, even slower, then it's going to limit your ATP. So glycogen phosphorylase, that's the enzyme that breaks down glycogen to get glucose. So you have PFK slowing down, glycogen phosphorylase slowing down, as well as oxidative enzymes. these are deactivated by high hydrogen ion concentrations. So I suggest get into your textbook. It talks all about this kind of stuff, what hydrogen ions do in the case of fatigue. So hydrogen ions attach to these enzymes and change their size and shape and ability to function. So you're interfering with enzymes that supply that glucose. You can't get the glucose, you're not going to make energy fast enough. And that's your muscles reaching fatigue. So also inhibits cellular release of fatty acids. So think of this, it's a double whammy. You have hydrogen ions interfering with access to glucose, and you also have hydrogen ions interfering with release of fatty acids. So your body, your muscles are like, well, I can't get glucose, so I'm going to try fatty acids. Nope, not going to get that either. So you're creating greater reliance on glucose at a time when glycogen breakdown is inhibited anyway. So these hydrogen ions are basically just shutting a muscle down. It won't contract. So phosphoprotein breakdown is accelerated. So you still have that avenue, right? But how long does that last? How long can the phosphagen system be emphasized? Yeah, about 10 seconds. So pretty difficult situation. So faster depletion of substrate for ATP regeneration. So it's an ATP issue. Your hydrogen ions or acidic state is leaving you with very limited options for ATP production. So what does training do then? We go out and we train really hard. Are we able to continue? Are we able to deal with hydrogen ions more effectively? Yeah. That's why we train. That's why we do all this conditioning, because we're able to deal with acidosis much more effectively. So we're able to continue longer than we would have otherwise. Okay, so clearance of lactate. This is another slide that's brought out in your homework for the weekend. So again, lactate is not the problem. It's an indirect marker of what? Yeah, hydrogen ions is an indirect marker of those hydrogen ions. Lactate itself is an energy substrate. We use it to make ATP within cells, within other organs, heart and liver, and so on. So what this slide is saying is that lactate levels return to baseline relatively quickly, up to about an hour. This even shows within about 20 minutes, with a slow jog, you're down to about 11, within 11% of what they are at baseline. So lactate is kind of an indirect marker of acidosis due to hydrogen ions. So you could almost say that clearance of lactate would coincide with restoration of pH levels, because hydrogen ions directly affect pH levels. So this would kind of give you an idea if lactate and hydrogen ions are produced in proportion, they would also be cleared in proportion. So your pH levels would be restored within minutes in a recovery period. So what this says is maybe a continuous self-selected jog would help restore pH levels faster than maybe just a passive rest would, is what this was saying. Okay, so any questions on chapter 3? Okay, you ready for chapter 4? Okay. Well, let's dive in. So chapter 3 was all about anaerobic, so chapter 4 is all about aerobic. So we're in the nice steady state exercise with this chapter.
So what was chapter 2 then?
The what?
Chapter 2?
Chapter 2 is metabolism. So yeah, so chapter 1 was the introduction, all the training principles. Chapter 2, metabolism. Chapter 3, anaerobic. Chapter 4, aerobic. So we're going to dive a little more into how the aerobic system works with this chapter. Okay, so we know aerobic metabolism starts to predominate about 2 minutes and longer. Okay, so oxidative type metabolism, oxidative phosphorylation. So you remember right at the end of, towards the end of chapter 3, we talked about the oxygen deficit happens at the beginning of exercise. And so for about 3 minutes during a warm-up period before our bodies are warmed up, we have to utilize some anaerobic sources of energy. And then once our muscles are warm, we can go ahead and mostly emphasize the oxidative. So after that initial deficit period. Then after exercise, the excess post-exercise oxygen consumption. So if I asked you what EPOC stands for on the next exam, that's a hint. You should be able to have excess post-exercise oxygen consumption. That's the after period where we're spending lots of fat calories. So how do we measure oxygen consumption? Yes?
So if we're like doing a warm up, we use some of the anaerobic, and also at the end when we reach threshold, we also use it.
At the end, the epoch period, we're oxidative dominant. And that has to do with the shift in fuel source to fatty acids because they require more oxygen. So during the initial period, it's like your car. Your car's warming up. Our bodies, our muscles are like engines. And so after about 3 minutes, our oxidative system is operating at a rate that can support the exercise intensity.
And then when you hit ventilation threshold,
then once again you're getting into anaerobic.
So does it like recharge when you're in oxidative then? Because you're using it before and after?
Yes. Yeah, so it would recover. So the ATP PCR system can, and you're not maximally depleting the anaerobic because the intensity is pretty low to begin with in the oxygen deficit period. So recovery of those energy systems would be relatively fast. So, good question. Thank you. So, one of the primary goals of, at least in a laboratory setting with aerobic exercise, is to look at how much energy. So, how many of you have ever noticed on a treadmill or stepper or elliptical, you kind of look at the digital readout and you're looking at how many calories. So how many calories you expend. You kind of wonder about that. So in this chapter, we're going to go over exactly how we're able to estimate calorie expenditure during aerobic exercise. So there's 2 different approaches to this. In a laboratory setting, we have direct measurement of oxygen consumption, which is one way. In a more sophisticated setting, we can look at heat production, because aerobic metabolism releases heat as a byproduct. So aerobic metabolism can be assessed by measuring oxygen consumption or heat production. So oxygen consumption is a lot easier to measure, and so the system that we have is known as open circuit indirect spirometry. You don't hardly ever see the calorimetry anymore because it's expensive. It's in like a special room that has water circulating around the room. And so the heat that the person releases as they exercise actually heats the water that's circulating around the room. So the temperature change in the water is used to estimate how much energy. So it's really not practical, hardly ever used anymore. Most exercise physiology labs, including ours, use the open circuit indirect spirometry. So spirometry, you can calorimetry over here that measures heat, and then in terms of spirometry, we utilize this approach. So you're inhaling air from the room, and we know how much oxygen is in the air. We also know how much carbon dioxide is in the air. There's some carbon dioxide in the air you breathe. So what percentage of oxygen is in the air in Billings, Montana, which is only 500 feet above sea level? It's almost 21%. Okay, so almost 21%. So carbon dioxide is about 3%. So we know how much oxygen and how much carbon dioxide is in the air we breathe, and then we simply measure through a gas analyzer the oxygen, carbon dioxide that you expire. So we take the difference between the two. If we know how much oxygen you're consuming, and we know how much oxygen is left over in the air that you exhale, we take the difference, and the difference represents how much your muscles are taking in. So that's how it works. So the expired air, okay, so that's what these masks are. Maybe some of you have been around the lab and seen people being tested wearing these masks. This is the same system that we have. So the K5 system, you can take measurements outside the lab, which is really nice. If you know the oxygen and carbon dioxide concentration of the air you're breathing in, then you can measure the oxygen consumed and carbon dioxide produced in the air that you're breathing out. So it's just taking the difference between those two. So then in order to get to the amount of energy expended, assuming the exercise is near steady state, it's pretty easy. For every liter of oxygen consumed, we expend about 5 calories. It's not exact, and it kind of depends, but it'll go down to 4.9 something, but it's a lot easier just to say, okay, 5 calories for every liter of oxygen consumed in a steady state. So this is our lab a few years ago. Anybody remember this little room? Or you may have had the 106 class in this little room. Guess what we do with this room now? It's over in the PE building. It's our canoe room. We keep all of our canoes in there. So if you go in there, there's like 18 canoes stacked up. So now we have this nice lab over here in this building that we love. Okay, so this is one of our athletes from a few years ago doing a VO2 test. So open circuit, indirect spirometry, knowing the oxygen concentration of the air we breathe, 20.93%, so again, almost 21%. Carbon dioxide content is 0.03%. So very small amount of carbon dioxide, less than 1%. So the big assumption with this is that it has to be rest or steady state. So once you go above that anaerobic threshold, the amount of energy expenditure will be underestimated. So it's really accurate under oxidative conditions, but once you increase intensity enough to where you're above anaerobic threshold, there's different methods that you have to use to measure the anaerobic part of energy expenditure. So the first part of that, oxygen consumption, okay, the dot over the top means it's per minute. So anytime you see a dot over the top of a letter, that means it's a rate, usually per minute. So the equation is the amount of oxygen inspired. Okay, so the total amount of oxygen you're breathing in minus the amount of oxygen expired, like that. So what you're left over with when you take this, okay, so oxygen you breathe in, oxygen that you breathe out, what happened to the difference? That's what your muscles are using, right? So it makes sense. So ultimately, under a maximal exercise test, that difference would represent your max VO2, the maximum amount of oxygen you can use. So carbon dioxide, also important. So this would equal the amount of carbon dioxide expired minus the amount of carbon dioxide inspired. So we're also breathing in a certain amount of carbon dioxide, very small amount, with the air we breathe when we breathe in, but the amount of carbon dioxide that we expire goes up with increasing exercise intensity. So remember, we have metabolic production of carbon dioxide in the breakdown of glucose, pyruvate to acetyl-CoA, Krebs cycle, and so on. We produce carbon dioxide. So that's what we're measuring in the air that we expire. So again, the dot represents its per minute. So here's your actual equation. So the VO2 consumed represents the volume of inspired air multiplied by the percentage of oxygen inspired. Okay. So out of the total volume of air has about 21% oxygen. So the total volume of air that you breathe in multiplied by 0.21, because 21% oxygen, minus the volume of air you breathe out, okay, the volume of air you expire, multiplied by the oxygen in the air you expire. So the difference represents how much your muscles and other cells in your body are consuming. CO2 production, on the other hand, is total volume of air you expire multiplied by the percentage of CO2 in the expired air minus the total volume of air you inspire times the carbon dioxide in the inspired air. So we have software that does this. So hang with me here. Okay, so what we're looking at here is two different states, rest and walking. Okay, so rest for 1, 2, 3 minutes, and then walking at a steady state. So in this case, this individual was walking at 3.5 miles per hour. How many have done that on a treadmill? It's a nice brisk walk with 7% grade. So nice steady state. Okay, typical cardio type stuff. Okay, so percent of oxygen, percent CO2. So what did we just say? What's the percentage of oxygen in the air we breathe in? 21%. Okay, so what's being reported here is the percentage of oxygen in the air that's expired. Okay, so why would the percentage of oxygen in the air we expire be less than 21%, even during the rest period? You're using some of it, right? So the air we expire is going to have less than 21% oxygen. So the air we inspire has 21%, nice clean air. Okay. Our body uses some of that oxygen we breathe in, and then the air we breathe out is also going to have a percentage of oxygen with it, but it's going to be less than 21% because we're using some of that oxygen. So does that make sense to everybody? The percentage is going down a little bit from 21%. So let's see. So now we go from rest, which is in this case reported just standing, to where we're walking, but it's a steady state. Okay, so now we're using even more oxygen. So how can you tell from these values, albeit steady state, that this person's using more oxygen? Because the percentage in the expired air is going down even more, right? So you're breathing in air that has 21% oxygen. You're breathing out air that has less than 21% because you're using some of it. Okay, what about carbon dioxide? You'll notice that under resting conditions, the expired percentage of CO2 is around 3%. Okay, but what happens during exercise? We start to break down glucose and other fuel sources. We start to make some carbon dioxide as part of metabolism. So what happens to the percentage of carbon dioxide in the expired air as we go from rest to exercise? It starts to climb up a little bit. So that's what makes sense. So can everybody see? Is everyone clear on what this means? So really, if we go beyond steady state, what would you see in these percentages? Percentage of oxygen would continue to drop, right? Because we're using more of that oxygen ultimately where we reach our VO2 max. The percentage of CO2 would continue to increase because we're going to be using more glucose and continuing to produce CO2 through metabolism. Okay, so let's go through some exercise categories. How are we doing on time? 11:40. Okay, all right, let's go a little bit, maybe 10 more minutes. Let's go about 10 more minutes. You know, the weekend's coming up, you're excited, so we'll get this over with. So do you remember categories of exercise from chapter 1? Okay, so there were 6. So let's look at the cardiovascular response here, oxygen consumption. So we have this gradual ramp up period. So this would be corresponding to the oxygen deficit period. So after about 2, maybe 3 minutes, we reach this nice plateau in oxygen consumption. So that implies that we're in this steady state. Nice flat, oxygen consumption isn't changing. Okay, so category number 2, remember, long-term moderate to heavy exercise. Okay, so the steady state level is much higher, still steady state, but after getting up to about 50 minutes, we have this drift, this oxygen drift. So what causes that? So I noted some page numbers there, but I want you to get in and look at your textbook. It's caused by a few different things. One of the major things is an increase in body temperature. So hydration is really important because that helps us maintain body temperature. Another factor is release of hormones. Okay, so catecholamines, epinephrine, norepinephrine, and so on. Another factor, especially if we're starting to approach the anaerobic threshold, is maybe we're starting to drop pH just slightly, which would tend to cause this exaggerated response in oxygen consumption. So again, page numbers noted there. Make sure you look over that. Okay, so incremental exercise to maximum. So this is a VO2 max test. So what criteria define VO2 max? So as we do this in our lab coming up in November, mid-November, just before Thanksgiving. Okay, so I don't want to make you do a VO2 test right after Thanksgiving. Get it over with. Okay, so we're talking about right here. Page 100, middle of the column. So I really want to encourage you to get in and study your textbook. So a few different factors. So you need to be familiar with these. A lactate value greater than 8 millimoles per liter. Lactate value greater than 8 millimoles per liter. That's factor number 1. Lactate value greater than 8 millimoles per liter.
How many? 80?
8 millimoles per liter. Factor number 2, a heart rate plus or minus 12 beats per minute of a predicted maximal heart rate. So you're within 12 beats of a predicted max heart rate. Well, how do you know how do you get a predicted max heart rate? Is there a common equation?
220 minutes.
Yeah. So there's other equations, but the common one and the easy one to remember is 220 minus the age, which works pretty well for most people. So 220 minus your age, you're within about 12 beats of that, and that's one of the criteria for reaching your VO2 max. So factor number 2. Factor number 3, a respiratory exchange ratio of 9 or 10. So how many of you, maybe in a different class, have looked at the respiratory exchange ratio scale called the RER scale from 1 to 10? And so 10 is a maximal intensity, 1 is resting or very, very light intensity. So respiratory exchange ratio is subjective. So how many of you have ever done a workout where you're not really measuring anything by numbers, but somebody will tell you, I want you to give about 80% on this one. Okay, that's subjective. That's subjective. Give me about 80% of your max. So the RER works the same way. So during an exercise test, you can rate your perceived exertion based on this scale from 1 to 10. So you're getting within the last few minutes of the test, you're going to be feeling that you're almost there. So it's your own perception of exertion. So it's a scale from 1 to 10 that just characterizes your exertion. So 9 or 10 on the RER scale. Okay, so the very last one. So 4 factors. A plateau in oxygen consumption. The plateau in oxygen consumption is considered to be the primary criterion for obtaining a true maximal test. So those 4 factors. So what do you see here? This is almost like it starts to decline at the end, but there's a plateau. So it's almost like oxygen consumption is like you're climbing a mountain. Oxygen consumption over the course of time with increased intensity continues to increase, and then within the last few minutes of the test, it's flattening out or even dropping just a little bit. That's the key factor, is your body's not taking in any more oxygen, which makes sense because that's what a VO2 is. So once you're not taking in any more oxygen, you know you've reached your max. Okay, so this is what we call this is not a test we do in our lab, we do the Bruce protocol, but the textbook has a few examples with the modified bulky protocol. This protocol, you get to pick your speed. So it's walking. Okay, so normally 3.5 miles per hour, or it's your preferred walking pace, but every minute the incline goes up a degree. So you can see here the percentage incline with each passing minute is going to increase. So it's not so much the speed, because the speed doesn't change. It's just every minute you're getting more of an incline. So that's the modified bulky protocol. So constant self-selected speed, which I really like, because some people are fast walkers, other people are naturally slow walkers. But then it's just the change in incline is what determines the intensity, really. So here's an example from your textbook. This was using the modified bulky protocol. One of the downsides of the modified bulky protocol is it takes a long time to finish. Okay, so you can see in this case, male, 22 years old, 66 kilograms, temperature, pressure, humidity, all reported there, but 26 minutes to finally top out in VO2 max. You can see the VO2 in milliliters per kilogram per minute. And so you have to imagine with every passing minute, the incline is creeping up. So he topped out here at about a 25-degree incline, which is a lot. That's as much as our treadmills in the lab will do, is 25 degrees. So for a really fit individual, it's probably not the best choice because they're going to get up to those really steep inclines. So Bruce protocol is probably a better choice because that test generally, for most people, that one will take about, for really fit people, between 16 and 18 minutes. For other people, it's over with between 12 and 15 minutes. So milliliters per kilogram per minute, you can see oxygen consumption gradually climbing until the very end, 71.06, which is really good. So this is probably an endurance athlete, which is probably why the bulk is not a good choice, because they're going to go a long time. Okay, so static exercise. So I want you to take a look at this green line right here. This green line. So you've got rest, and then you have this 3-minute period of exercise, and then you have the recovery period. So this green line represents the VO2. So anytime you see VO2, think oxygen consumption. So what does it look like? With exercise, the oxygen consumption is gradually climbing, but then after exercise, you get this tremendous spike before it begins to drop back down again during recovery. So what is static exercise? What does that mean, static exercise? Not a lot of movement, so a plank. How many of them planks? Yeah, planks to death. Okay, so static exercise, you're not really moving, so you're tensed, muscles are tensed. That's what static exercise is. So I'm not sure exactly, I'll have to look to see if they reported what was actually being done here. But with static exercise, the blood flow into a muscle is somewhat blocked because you have muscles contracting that are compressing capillaries. So in other words, you're getting lesser amounts of oxygen into the muscle while a muscle is contracted. So how it works is, aside from static, they put static aside for a moment, you have 3 different types of muscle actions, kinesiology students. So what are they? You're lifting a weight, which is what? Concentric. You're lowering a weight, which is what? Eccentric. So what happens during traditional repetitions is that you're squeezing blood vessels when you lift weights. So muscles are contracting, which is limiting the oxygen delivery into muscles because capillaries are compressed as muscles are contracting. And then as you lower the weight, you're releasing that compression on the capillaries. So it's almost like you're compressing capillaries and then releasing during the lowering phase, restoring blood flow into the muscle. So you go through these cycles with each repetition. With static exercise, it's just one period of this compression. So you're not completely limiting blood flow, but blood flow is less because of this compression on capillaries as muscles are contracted and tensed. So what happens is after you release that contraction and now you're in the recovery period, muscles are now relaxed. So what's happening with blood vessels? They're no longer compressed anymore. So what's going to happen to oxygen delivery to those muscles? It's going to go up, which is why you see this initial spike for about a minute until that blood flow delivery is normalized, and then things go back to baseline. So with low level static type contractions that in this case 3 minutes long, you're not going to be able to do a maximal isometric contraction. You're not going to be able to hold that for 3 minutes. So we're talking about low grade isometric contractions for 3 minutes, similar to what you would see on a plank for 3 minutes. Okay, so there's tension there, but it's not maximal. Compressing blood vessels just a little bit, then you release it, and you get all this oxygen delivery, which is what the spike is there. Okay, so that's probably enough for today. So, do you have any questions? Okay, so we've got homework this weekend, lactic acid stuff, so that's due on Tuesday. We'll continue with chapter 4 again, and we're doing blood lactate in lab next week. So for For some of you, I'll see you in a couple of hours for the stair test. So we'll meet in the lab, we'll talk it over, and then we've still got good weather, so we're gonna go over and use the steps at the liberal arts building.